Hello, welcome to another concept session, and we're going to today talk about kinematics. Kinematics is a really very important part of learning mechanics. If you mess up kinematics, you probably messed up the rest of the stuff. Okay, so if you have any doubts about what we're going to talk today, at the end of what we have talked, you're still confused about it, then you should go back and watch it again or read from another book and make sure that you can do any kinematics problem thrown at you before you can proceed in mechanics. Okay, so this is where your vector knowledge gets really applied. All right, so the kinematics, basically you have these four quantities: displacement and position, velocity, and acceleration. So these are called so-called true vectors, and this is a vector where one point has been chosen. It is tied to a coordinate system. For instance, this is tied to a coordinate system. So it's special to a coordinate system. But everything else is the other three concepts, although we use coordinate system to work with it, but they are independent of coordinate system. Okay, so these guys are independent of choice of origin, wherever you try to place the origin. But this one is depends on choice of origin. This is also a vector, but with that caveat. Okay, so somehow we can distinguish them. All right, so what are these quantities? What are these quantities? You really need to be able to distinguish and have a very good idea. Okay. All right. So displacement. Let's look at displacement. So if you watch an object move, like a car moving around, so they may be moving around like this. So it's here. So it's here at some time t1. And maybe it's over there at time t2. So it may be on a road or on the surface of the earth or in a space, whatever. Okay. So if you draw from here to there, so this is so-called here. Let's call it point P1. We might call it's here, there, and point P2 might call this colloquially there. So if you go from here to there, this vector, that's the vector is called displacement vector. So here to there is called, this is the name of it. That's it. That's just name, displacement vector. So you can see that it will depend on the time t1 and time t2. So that vector is different than if I was from here to there. This displacement vector will be that. Another thing to notice is actual path was this. This is the actual path. But the displacement vector is independent of the actual path. It's just here to there. So this is different from actual path. That's very important. And if you want to capture the actual path, we'll have to use what is called position vector. All right, that's why the position vector is important. But this position vector is very important also because as the suppose I stay here and the there becomes, I keep coming down. So I said not there, not there, not there. Maybe there is that place, that place, that place. As you get very close to it, then we can use calculus to define a quantity which are like infinitesimal displacement. So you can say there will be something called infinitesimal displacement. Infinitesimal displacement. Now this will capture the actual path. Capture the actual path. Because infinitesimal will be when T2 arbitrarily close to T1. So here and there are more or less almost the same thing, but not exactly same point. They're arbitrarily close but not exactly on top of each other. So then we say if they're on top of each other, then there's zero displacement. But if they're not on top of each other, there will be tiny difference, and that tiny difference we'll call it infinitesimal displacement. If it's moving, if it's not moving, then T1 and T2, even they may be different, displacement still will be zero. So the motion is captured by infinitesimal displacement. Okay, the infinitesimal displacement is what, if it's non-zero, it captures the motion, and that's why it's important for the rest of the things which are associated with the motion. Okay, now that was the geometric picture. This is the most fundamental picture, but we want to be able to do it analytically, so that a vector can be done analytically, right? Analytically, when we say analytically, we usually say, okay, pick a coordinate system and tell me things like, actual coordinates. So if I pick a coordinate system, let's see, we are in a three-dimensional space. You have x, y, and z. Then this thing over here, it will fall somewhere here and here. So this will be like some p1 and some p2. So this vector, if you look at this vector over here, the magnitude of this vector is actual distance along that. So we do need some kind of a unit of distance. We need a unit distance to tell how far apart P1 and P2 are in space. So that's the magnitude is actual distance. And then the direction is going to be simply here to there. You got to tell me here is the point P1 and here's the point P2, and it's that direction. They can just in words. You just describe in words and pictures. Over here, you can see in analytically, we have the same vector, but we can write down the distance if I know the coordinates of this guy. So it says the coordinates, this is x1, y1, z1. And coordinates, this is x2, y2, z2. So what the distance will be, actual distance, let's call it s12 for this distance. So s12, and we can call this vector, can give this vector a name, s12 vector. So the magnitude without the arrow written down, so this is the magnitude. Magnitude will be equal to square root of x2 minus x1 square, difference of x coordinate, difference of y coordinate squared. This is coming from Pythagorean theorem, right? And z2 minus z1 square. So you can see, if you're not clear about where this comes from, you can just work out, say in xy coordinate, and if you have a point here and point here, then you can see that there will be a right angle triangle. This will be, this is point 1 and point 2, so this is x2 minus x1, and if you drop on this, guys, this will be y2 minus y1, and this distance will be the hypotenuse of this triangle. And you can work out the similar triangles similar way here, and in 3-dimensional you are going to get something like this, right? Now what will be the direction? So I got the magnitude. What's the direction? The direction, now if you have a 3-dimension, what is the, how do you tell direction of something in 3-dimension? You can use a spherical coordinates, so you can place the vector, and so you can get the angle theta and phi as a spherical coordinate. That's the normal thing. So we can use spherical coordinates, theta and phi, and I'm going to give an example of how to do that in 3-dimension. If you're in 2 dimensions, like over here, suppose I had points that at z equal to 0 plane, so the direction of this vector, if this is the vector we are talking about, the direction will be this, the direction of the positive x-axis. So this is the direction of the positive x-axis. So with respect to that, this vector is that angle. We'll call it angle theta. Normally people use an angle theta for that when you're in two dimension, but in 3-dimension that angle will be called angle phi. So another letter will be used. So you can get from here, the direction can be just this can be a proxy for direction in 2-dimensional situation. And you can see from this triangle, you can say arctangent of delta y over delta x, delta y over delta x. That's going to be the theta. So that's the angle we'll use as a proxy for telling the direction. And we're always going to tell the direction with respect to the positive axis, positive x-axis. Maybe almost always. Sometimes we might say, okay, what's the direction with respect to the negative x-axis? What's the direction with respect to the positive y-axis? Any of those angles will be okay. All right. So let me. This one is very easy for you've probably seen it before, and it will be most common in most problems. And you want to make sure that you understand that. And let's do some examples of that, and then come out to get direction of the 3 dimensions situation. Okay. Okay. So let's look at a numerical example, and you can convert that to symbolic things later, on your own. So how do we tell the direction of this? Of course, the magnitude is very easy to tell. So magnitude is, we have a formula for it, and you can just say this distance was going to be made up of this guy, 3 squared plus 4 squared plus 6 squared, and that's going to be this, going to be 25 plus 36 is square root of 61. That's going to be the magnitude. How do we tell the direction? By giving angle with respect to the positive x-axis of the projection. We take this point and drop a 90-degree on the xy plane. Okay, so on that, if you so this is the point P at the end. So this, when it drops it, let's call it ends at point Q, and we drop into x-axis, let's call it R, and so that will hit, this will be at 3 units because of the x-axis. When I draw the same projection, the y-axis is going to hit at 4 units on the y. And here is a diagonal, and that diagonal, when you draw from there onto their 90 degrees, this will hit 6 units because of 6 there. Okay, so this is the angle that we call it phi, and this angle we call is theta in the spherical coordinates. Physicists use like this, and mathematicians actually call this guy theta and that guy phi. So I'm not going to use a mathematician's notation. We're going to use the physicist's notation. So if we look at the phi, it's again right angle triangle, 4 this side, 3 this side. So it's just a right angle triangle. This is 90 degrees, and we want this angle. So this is the perpendicular, and this is the base, and this is the phi we want. So this over this. So tangent phi just turns out to be like y over x, and then just 4 over 3. And from there I can get phi is, I think, close to 53 degrees or something like that. And when you look at this over there for theta, theta is almost the same way. 90 degrees is here, and so this thing diagonal, which is same as that, from the way I've written down 3 and 4, from there this is 5, which is same as that of 5. So this is 5 and this is 6, and this is the theta. So tangent theta will be just 5 over 6. Or if you want to use this value, so that this is square root of 61. So you could do sine theta will be 5 over square root of 61, or cosine theta will be 6 over a square root of 61. Any of these angles can be used, any of these equations. So I looked up 13, this is 39.8 degrees, and all of this is the same thing. Okay, so that's how you do the three-dimensional vector. Use spherical angles with respect to the axis that you have chosen to tell whether the direction. You always draw the vector starting at the origin. So if the vector was over here, you kind of make it over there. Translate the vector, keeping the direction the same, put it at the origin, start from the origin. So that's your displacement vector. All right. So what is the position vector? Position vector is a displacement vector with respect to the origin. All right. Let me illustrate. Okay. So position vector is origin is playing a very important role. Origin is playing a very important role. And it's also only one instant. So here is a object maybe moving like that, and you picked a coordinate system like that, and this is your origin, and at some time t it's over here, and of course it's moving around, so it is used to be here. It could be standing there forever, whatever, but this is, if it's moving, it's, say this is the path, also called trajectory. So at different times it's different place if it's moving. And if I draw, so this is an abstract vector, unlike the displacement vector. It goes from here to there. So this displacement, the particle is not displacing in this manner. It was never over here in this way, right? But we're taking one of the things fixed. So this is some position P, and it's going to have some x which depend on time t, and y some time t, and z time t. So if we want to do, because already chosen the coordinate system, at least the origin of the system we have chosen, then we can think analytically, this vector. So this distance will be some r, some spherical r will be same thing. That will be the magnitude of this vector, and the direction will be the same way. If this was x and y and z, you can just do this, and so this will be xy, and that from this parallel to that's going to be z. This going to be z, and you can, for the direction, you can use the phi and this as a theta. So you can just do as before. So this is called position vector, and its components. So we can say position vector usually is use letter R for that. So this vector, because the distance is going to be used letter R, we can use R and overhead to call it position vector. So vector denoted by just the arrow, and you can write down x of at some instant. So this is actually a function of time. So this is kind of abstract way to write, and this will be more explicit way to write y of t j hat. These are the, like, this is direction, unit vector is I hat, and this one is a j hat, and this direction is k hat. So these are unit vector, and z of t k hat. So this we call it decomposing into components. These are the components, and this multiplying unit vector. So this is vector along the x-axis, this is the vector along the y-axis, and this is vector along the z-axis, and they add up in a vector fashion to give me the abstract vector. We're going to call it position vector. And so because I hat, j hat, and k hat are kind of fixed in our calculations, we can also write this as you would write any coordinates z of t. So these are like, I can give me this, I can construct the vector from there. And sometimes we just omit t, we just write x, y, and z for the position vector. But in our mind, we know that this depends on time, because at different instant the particles or object is at a different place. So this is a position vector. Position vector is always with respect to some origin. Okay, so position vector plays an important role in building up velocity and acceleration, because we want to know displacement, infinitesimal displacement. So using position vector, we can actually talk more about displacement and infinitesimal displacements. Okay. Okay, so how is position vector related to displacement? So how is R related to displacement vector? Now this one have two times, t1 and t2, and this one is only time t. So we'll say, okay, let's call this one, let's call this is at time t1, let's label this r1, and pick another time t2, and so this will be the position vector at that time r2, right? The displacement vector from our previous discussion is this. This is the displacement vector, and we're going to call it from 1 to 2 with an arrow, going from 1 to 2, and we're going to use the letter S for the displacement vector. So you can see that I have three vectors. You have R1 vector here in that direction, and the displacement vector this way, and then I have a final vector that way. So in that, if I start from here, go here, and then I continue that direction, and this one coming from here and reaching to the same place. So clearly in that this triangle, if you using from the previous notations, you can see S12 vector, and this is R1 vector, this is R2 vectors. So this vector equal to sum of these two vectors. So S12 vector is equal to R2 vector minus R1 vector. So this is actually subtraction of these two. So from this triangle diagram of different vectors in different notation, different directions, you know the displacement can be obtained from the position vectors at those two times. And what's a displacement vector? Let's illustrate the infinitesimal displacement vector using this notation. Okay, so let's draw a new thing. So here is the particle's path is moving in this thing. So at one instant, at some time t, it's over here. So we label its position vector by this. At a very infinitesimal time delta t later, it's over here. So its new position, we're gonna say it's so this, I'm treating this r as a function of t, and now the t value will be t plus delta t. Sometimes r plus r of t plus delta t is a position later. So when I draw a direct arrow, that's going to give me infinitesimal vector. So we used to we were labeling s as a displacement vector. We're not going when we draw infinitesimal, we don't use this letter s. We use same letter r, but we just call this delta r. So we're going to use this for the infinitesimal displacement as a delta r. This is just a abstract notation. That's about it. Just a name for an infinitesimal vector. So in this thing, you can say that delta r, which is infinitesimal displacement vector, is going to be equal to the vector position vector at t plus delta t at this instant. It's not a multiplication, it's at this instant, not multiplication, not multiply. It's not a multiply like r times that. No, it's r at that, and then r at t. And you can see that this is a in delta t is going to 0, but not delta t equal to 0. So there's always going to be a little difference in time, and that's if the particle is not moving, then r will remain the same. But if the particle is moving, there will be little different place, and that difference is what we are after, because we're trying to capture motion when we study kinematics. Okay, so that's the displacement. This is the infinitesimal displacement, and turns out to be a very important, extremely important concept. Because when we study how fast something is moving, all I have to do is divide this by this delta t. Okay, so velocity will come out to be velocity vector, which is a vector quantity. We're going to use the letter v for it. We are going to call it instantaneous velocity, and which is how fast something is moving. So I have this much displacement in that much time, and we have infinitesimal time. So we say limit delta t goes to 0, and so this is this quantity, whatever it will come out. Of course, if it's not moving, then this will be 0 vector, right? So if not moving, then delta t is never 0, so I'm never dividing by 0. So delta t is never 0. Yes, tending towards 0, but never 0. And a lot of people just look at this and then confuse that. But if it's not moving, then a numerator delta r, in that instant, it will be a 0 vector because it didn't move anywhere. Then 0 vector by non-zero delta t, limit delta t goes to 0, is just going to give me a 0 vector. So the velocity in this case will be 0 vector. So the velocity in this case will be a 0 vector. So that's why we say velocity is a 0 when something is not moving. But if it's moving, then it's not going to be 0. So how do we, this is conceptually very abstract. So how do we actually make it more concrete and more analytic? So when we go back and look at this analytically, what we're going to see is delta r has some x component and some y component. So x component is like x at t plus delta t minus x at t. That's the x component on the right side, and the y component is y t plus delta t. At that instant, what's the y-coordinate the object is over here? When it's over here, what's this y-coordinate? Minus y when it was over here. And z will be the same way, t plus delta t minus z at t. I know a lot of times when you study, you just study one dimension, two dimension, things like that. I like to just study the whole thing and then reduce. If it's problem is one dimensional, just do one dimension. But conceptually, when you're learning, learn the whole thing. Okay, that's way better. So now this is this actually I'm going to get some numerical values here, right? And depends what delta t is. You don't have to put numeric numbers, but I can imagine they will be very concrete. Unlike this thing, this is very abstract. So from which I can get the magnitude and the direction. Now, if I divide to get a velocity, so this velocity vector will be just limit delta t go to 0 of, I gotta divide this by delta t, this guy divide by delta t, this guy divide by delta t, and this guy divide by delta t. So when I take this limit, if you look at what happens when you divide by delta t, in calculus, you know, you t plus delta t and x at t divide by delta t, and I'm going to take a limit delta t go to 0. This is nothing but the definition of the derivative dx over dt. So velocity or instantaneous velocity as velocity at time t. So sometimes people write v at time t like that. Not multiplication, is just indicating at instant that. So that's equal to, it's going to have x component given by this derivative, y component given by this derivative, and z component given by this derivative. And Newton introduced a notation for writing this derivative. Just put a dot over it. Newton used to say, write it like the x dot, y dot, and z dot. Sometimes we like to just continue that notation. It has its pluses and minuses because it kind of hides what you're trying to do. It's just symbolically representing the derivatives. Okay? But it's a shorthand notation for derivative. Okay, let's do an example. Okay, so here is a simple problem. So I'll give you a position vector in giving the coordinates with respect to time, and z coordinates is not changing, so the motion is happening in xy plane. And so what is the velocity at time t equals to 2 seconds? So this thing is in meter if t is in seconds. All right, it's a very easy problem, right? So all I have to do is take v, this different ink, maybe this one. So v is equal to, take a x derivative, a time derivative of this, so this becomes just a 3. The time derivative of this is minus 10t plus 25, and time this of course 0. And so this is at time t. So I want to evaluate that as velocity at 2 seconds. Not multiplication, okay? Not multiply. It's just at this point. So just t equals to 2, I put it here. And so I get this remains 3, and this means 4 and 0. And because of the units, this whole thing should be meter per second in terms of units, right? I need to get magnitude and direction. So of course the z is not equal to 0, so I can just look in the xy plane. So it's 3 here and the 4 here, 3 here and 4. It's kind of like that. Okay, so I can give this angle for direction, and the magnitude will be the length of this arrow. So the magnitude will simply be square root of 3 square plus 4 square, and that's 5. And this as direction I'm going to just angle theta is arctangent 4/3, which is look, I think it's 53 degrees. You can just check it. All right, close to. So that's how we can solve this problem. Let's do another problem. Okay, so this is another pretty standard problem. So something is moving in circle, so it's going around like that in that direction, and there is a coordinate system. It's in x and y plane, and at some instant t, so when t equal to 0, theta is 0, so it used to be here at t equal to 0, but at t it's over here, and this angle is theta t, and it's given to be theta t is given to you, and you're supposed to find what's the velocity at this point. Its velocity, of course, changing direction all the time, right? Because it's over here this way, and then over this way, and then over there the velocity is that way, over here the velocity is that way, but over here I need to get the velocity. So this is kind of arbitrary, so that will have information once you find this. Let's work it out. Maybe you can pause and you can work it yourself. So if I do velocity vector, and if I take a x component, take derivative of that, so this becomes minus r sine theta, and then I got to do the theta derivative dot. So we're going to use Newton's notation. Dot is d theta over dt, and then nothing else. So theta dot is just b plus at. So that's what that is. Don't have to put it in here, just over there can be fine. And the y will be r cosine theta, theta dot. So what's the magnitude of this? Z is 0, so I don't have to worry about that. So we have a vector which is which has this kind of thing. So we can do magnitude, which is v magnitude, which sometimes written as simply v. It can be square root of a square of this plus square of that plus square of that, and you can see the r square and theta dot will be common, so it's going to be r square theta dot square, and then I'll have a sine square theta plus cosine square theta, and which will give me 1 regardless of what the theta is, right? So this is 1, and so this just comes out, and this is just r theta dot, and so the r b plus at. So I didn't have to put that and clutter the notation. How about the direction? So I can use symbol theta for that. So this vector, I'm going to use direction with respect to positive x-axis, with respect to the positive x-axis. So I'm going to call this guy vx, v sub x, and call this whole thing v sub y. And for any vector, we're going to use the symbol, let phi be the angle. Instead of theta, I'm going to use a different symbol because I already used theta. So phi is going to be arctangent of vy over vx. Now theta will get r and theta will cancel out from both of them, and it's going to be arctangent of cosine theta over minus sine theta. Well, if this was a tangent, I would immediately cancel with arctangent, right? inverted, this is the inverse function of time. So somehow if you can write down tangent, that will be great. So this will be arctangent inverse minus cotangent theta, and you can see, maybe you have already done it, it will be tangent of theta plus pi over 2. So phi is actually theta plus pi over 2. So you can see that over here, the direction, the velocity is that way. So if I bring the velocity over here, it's going to be just 90 degrees over here. So if angle theta plus pi over 2, this is the angle phi, this is the velocity vector. All makes sense now, right? If I had a clockwise, I would get a this angle will be flipped over this side, but we are talking about counterclockwise. So this is a good example. Okay, finally we want to talk about acceleration. So we had a recall we had a displacement. We talked about displacement, and we talked about position, which was r at some time t, and the displacement of some s, which was a function of t1 and t2. And then we talked about infinitesimal displacement, which was r at t plus delta t minus r at t, which we wrote down as delta r, and it became infinitesimal because delta t was but not equal to 0. So it's tending towards 0 but not equal to 0. And then we took a ratio of that and we defined velocity, and we said, well, take the delta r and divide by this infinitesimal time and take a limit delta t goes to 0, and so this just became dx over dt, dy over dt, and dz over dt. These are components of this velocity vector, and we can, from there we can get the magnitude and the direction. So magnitude has a name for this. Magnitude of v is also called speed. And you just use a symbol v for it because we have magnitude for any vector. It's just the same symbol but without the arrow over it, right? So this is something I wanted to mention. Okay, now the velocity is also a function of time. It depends on, all of this. When you take a derivative, it will be a function of time, this will be a function of time, and this will be, in general, it may be constant, but in general a function of time. So something is moving about, and we can take a time t and some instant later, t plus delta, infinity later, we can say, what's the velocity here when it's over here? We'll call it v. What's the velocity when it's over here? Well, it will be a time a little bit later, because we know for all times what the velocity. If I know the position all time, we know the velocity all times. Well, when I compare it, will tell me how the velocity is changing with respect to time. So we want to know rate of change of velocity. So we'll have a v at t plus delta t and subtract v at t. So this will be infinitesimal change in velocity. Infinitesimal change in velocity. Again, delta t is go to 0, but delta t is not 0. Now, this much velocity is changed in that much time, but I want to know how fast the velocity is changing, then I have to take it, divide by delta t, just like I did over here. So we will call this quantity delta v, and we're going to, just like before in this case of the displacement, we are going to divide delta v by delta t and take a limit delta t goes to 0. So delta t is not 0. I'm not dividing by 0, just like over there. Okay, delta t is not 0. All right. Now this quantity tells me how fast the velocity is changing, and this is what is called acceleration vector, and you denote by a. So this is the fundamental definition of it. And now I go over inside here, and you can see we're writing this v sub x and components with a uniform notation. We have chosen to indicate the components of the vector with this coordinate label like this to the symbol, attached to the symbol. So this, if you look at this inside, it simply limits delta t go to 0, and the x component will be vx at t plus delta t minus vx at t over delta t, and the y will be the similar and z will be the similar. And if I take a limit of this, we clearly the derivative of the velocity. So dvx dt, dvy dt, dvz dt. So these are the components of the acceleration vector. X acceleration like that, and if I put in say x, y, and z, this will become give me same thing but second derivative, x over dt square, d square y over dt square, d square z over dt square. So this is the analytic, this is abstract definition of acceleration, and these are analytic way to say the same thing, but they require a coordinate system. This one does not require coordinate system. Doesn't require you choose coordinate system. It's just comparing the velocity and vectors. You're just kind of comparing pretty abstractly. So the acceleration is an abstract quantity, does not require any coordinate system. It's there, whether you have a coordinate system or not. But once you put a coordinate system, you can process it further. So this requires coordinate system. So when you work out these numbers, depends on the coordinate system. But when you get the magnitude, will be independent of coordinate system. So there will be magnitude will be a number that will not matter how you choose the coordinate system, and direction in space will not matter which way the coordinate system is pointed. Of course, the values of theta and phi will depend on which coordinate system you choose, because they are tied to the coordinate system. But the magnitude independent of coordinate system. So these are coordinate independent quantities. Let's do a couple examples that we did earlier, but in this case we figure also out acceleration. Okay, so these were two position vectors given, and in each case we want to find out the acceleration. We have already figured out the velocity. Let's do this one. You can do it and come back and see what I got and what you got. So first we have to go velocity vector at some arbitrary time, and that gives me, take a derivative of that, 3 minus 10t plus 24 and 0, and I do ddt of this guy, and I'm going to get a 0 minus 10 and 0. So this is the acceleration vector, and that just clearly tells it is magnitude is 10 meter per second square, and the direction is negative y axis because of that. So I didn't have to do much more work. Now this one, may require a little bit of work. So V was minus R sine theta. I'm going to just use a theta dot, and R cosine theta and theta dot and 0, and then I'm going to do d dt again. Let's do it over here, d dt of this again. So the acceleration will be, of course this R is independent of time, R constant, so minus R sine go into cosine, theta dot is squared now, one more, and then minus R sine theta, but two derivatives now, and this over here is R minus R sine theta, theta dot square, and then plus R cosine theta, theta double dot, and then of course the z part is 0. I want to get magnitude, just x and y, so I can get a magnitude and direction, which magnitude means I need to square this. So magnitude square will be square of this whole thing plus square of this whole thing. So this is ax and this is ay, so this will be ax square plus ay square, and I'm going to work it out and write it over here. Okay, after doing this calculation and using our theta that was given to us, theta that was given to us, you actually simplifies, but doesn't simplify very much, because the theta was varying quadratic in time. If the theta was uniformly varying, that would be uniform circular motion. So if you want to work out case this A and this A is different, right? This A is coming from there, so maybe we can write down little b and capital A, capital B and capital A, capital A. So over here it will be like a capital B, A, and capital A. So case capital A is equal to 0, meaning if just that, then it's pretty simple. Then at that point you have R square B square, and this goes away, and that just means A, magnitude A, it simply equals to R square R times B, square root of that. So this will become that, and so this is a pretty simple answer for that. And let's figure out the direction for this case only, because doing the direction for the more complicated case is just like a much more messy. Okay, so I will erase some of this and come back and show the direction of the vector that without when A is equal to 0. Okay, so I went ahead and did this when A equal to 0. So theta of t was dt plus half at square. Originally, when A is 0, then theta double dot or two derivatives of theta will be 0, and then the acceleration will simplify considerably, and calling that ax and ay. Now I used angle theta, so I can't use theta for denoting another angle, right? So I'm going to use phi just to denote the direction of this vector. You can use some other later. You can see maybe alpha or something like that. Maybe say alpha to denote this vector, because use phi for the velocity. And so after cancellation, it seems like tangent alpha is tangent theta, and you'll think alpha is equal to theta, but actually you have two answers. Basically what's happening is, so if theta is this way, this where the particle was, is this the theta, then you have to look at say this is positive and this is positive, then this vector is in this quadrant, actually is in that direction. So this thing is, that's the angle. So this acceleration, so this object is going in this circle, and when it's over here, then the acceleration vector is pointed in that direction. Only when theta is like that. When this theta is bt, not when theta is bt plus half at squared. We didn't work that one out. But when this theta is just this much, and that's a uniform circular motion. When you have a more general formula like that, a general case like that, your direction will be not along to the center as you're seeing here, and you probably know that this is called centripetal acceleration. We'll have much more, we're gonna have many more problems to do with this circular motion later on, but right now you can see just in kinematics how the definitions of position vector and velocity vector and acceleration vector, they all come together, and in an analytic solution is just not that difficult, just going through some little derivatives. Now what we're going to do is, suppose I get an acceleration given. Here all the problems we did was, given the position, how do I proceed towards the acceleration? In the next video we're going to talk about, given acceleration, how do we proceed backward? Can we figure out how to get the position and the trajectory of the particle in space? Okay, so that's what's coming up. You probably already guessed that probably has to do this. If one way is the derivative, so you have r to v to a, those are derivatives, and then you go in the other direction, another direction, that's going to be integrals. So that's the relationship, and we're going to explore that in the next video. Okay, that's enough for now. Take care. Bye.